from the University of Wisconsin-Milwaukee, who will be telling us about coarse embedding instruction. Take it away.
Thank you, Molly. Thank you to the organizer for allowing me to speak here. This is actually my second time in this workshop. I'm speaking. I spoke for the first time in 2019 when it was held in my university, Wisconsin-Milwaukee. So it's a pleasure to give a talk again. So I'll be talking about coarse embedding obstruction. So I'll start by defining what coarse embedding is. So coarse embedding is a map from between two metric spaces from X to Y with these two control function, rho minus and rho plus, such that the distance between f of x and f of y is bounded above by rho plus of distance between x and y and bounded below by rho minus of distance between x and y. And this proper condition is really needed for this rho minus function, which actually ensure that if you have far apart point in space x, then it has to get sent to far apart point in y. Okay. So what are the example? Well, isometric embeddings are coarse embedding, where this rho minus and rho plus, these two functions are just identity. Okay. More interesting example comes from this. So if you have a finitely generated group and it acts on a space x, a metric space, by isometry, and the action is proper. By proper, I mean if you have a compact set in X, only finitely many translate of that set intersect that compact set. So, so if you have a proper action by isometry on a space, then you can produce this map. You can choose first a point in X and you send group G to the orbit of that point by this map. G goes to G prime G dot X naught. And that map turns out to be a coarse embedding map. Then the proof goes just like the Milnor-Schwarz lemma. Okay. So now you can construct by yourself many coarse embedding. For example, Z2 acts on R2. So that means Z2 coarsely embeds into R2. Okay. So the motivating question for my talk, well, which this question I'll not talk about this throughout the talk, but that was the beginning of this project. So if you have a group, what is the minimum n so that G admits a proper action on a contractible N manifold? Okay, so how large your manifold needs to be dimension-wise so that a group can act properly. Okay, and by the previous example, we know that if in order for G to act properly on a space, it has to coarsely embed, and so it's natural to ask this question, which is weaker, for a given group G, what is the minimum dimension of a contractible N manifold where you can coarsely embed your group into? Okay, and so my talk is really about finding lower bound for this N. Okay, and why stick to a group? We can ask this question for general metric space. So if you, for a given N and a metric space X, the real question that I'll discuss in this talk is what properties of X obstruct coarse embedding into Rn for fixed N. Okay. Now, to get an idea, we first look at the property of X that obstructs topological embedding into Rn. Okay, so forget about coarse for now, and let's see what happens, what kind of obstruction we have for topological embedding. Now that goes back to Van Kampen. So let's start with the topological space. There's no metric there, it's just a topological space. The main construction here is this, starting from X, you can take the Cartesian product of X with itself, X squared, and there is a diagonal copy of X sitting inside that. And you look at the complement. So you look at this X squared minus delta X, which is really just pair of distinct points. And Z2, you have a Z2 action on that space. In fact, free Z2 action. So pair of distinct points, you can just flip the coordinate and that gives you a Z2 action. And so you can, once you have an action, you can take the quotient by this action. And that gives you a space which we call configuration space of X. Okay, so you X squared, you give it the diagonal, you have an action of Z2, you take the quotient. That's your configuration space of X. Now, so what happens? Let's say now you have a embedding X to Rn. From there, well, choose another embedding. We should be clear why we do that. Choose another embedding from Rn to R infinite, infinite dimensional space. Now, these maps will induce a map between the configuration space. Why? Because while configuration space is really just pairs of distinct points, and this function f is injective, and so is I, so it sends distinct points to distinct points. So you have a well-defined map between the configuration space, because this map also preserves the, well, this Z2 action. Okay, so you have a map on the quotient space between the configuration space. And once you have maps between the space, you can look at the induced map in the homology of this space. Okay, so I have this composition of maps going from homology of configuration space of R infinity all the way to homology of configuration space of X. Now this configuration space of R infinity is really is the same as RP infinity. It's not hard to check. So you have, so it's Z2 all in all dimensions. So H star of configuration space of R infinity is equal to Z2 in Z2 coefficient. So I should have said that earlier. All the cohomology I'm talking about here is in Z2 coefficient. So this cohomology is really the cohomology of RP infinity, and this cohomology is really of homology of RP n minus 1. So the RP infinity, you have Z2 in each dimension. So pick a generator for Hn of configuration space of R infinity. And also, as I said, configuration of Rn is really just Rpn minus 1. So this middle one is really the cohomology of Rpn minus 1. And so what you get is f star applied to I star of eta n has to be 0. Why? Because in this middle there is no nth degree homology, because this is just Rpn minus 1, so there is no homology there. So this composition has to be 0. Now the surprising fact is that map, this composition f star, f tilde star, composed I tilde star, depends only on X. This is intrinsic to X. This doesn't depend on F or I. So I can denote that class over here by Vkn of X. The Vk stands for Van Kampen, but the meaning of this notation is it's only depend on X, that class. So this is only, you can calculate this class without having any map to start with. And so the summary of this discussion is this fact that, so we started with an embedding of X into Rn, and from there what we saw is some class Vkn of X that vanishes. And so here you get an obstruction. So that class, if I give you a space X, and you can figure out the Van Kampen, you see the Van Kampen class of this X is not equal to 0. That just means X cannot be embedded inside Rn. Okay, so that's what Van Kampen obstruction is. Okay, so if X, in order for X to embed inside Rn, some class which lives inside the cohomology of the configuration space of X has to vanish. Okay. Now, well, the first thing we want to do is we want to mimic this construction in the coarse setting. Everything here was in the topological setting. So what happens if you try to do the same thing in the coarse setting? So if you have this metric space, and now you have a coarse embedding there. Now, in the previous slide, so the first thing we had a map between this complement of the diagonal to the complement of the diagonal. But here you might not have that map, because the coarse embedding might not be injective. So the distinct pair of points might not go to the distinct pair of points. Okay, and so you don't have a map there, but you can get rid of this problem by taking a neighborhood. You delete a neighborhood of the diagonal, and then look at the induced map. there you have actually a map, because the function f is coarse embedding. The far apart point does go to far apart point. So if you delete a neighborhood of the diagonal, that gets sent to distinct pairs which are at least r apart. Okay? For every r, you can get an s, so that any point s apart from the domain gets sent to pair which is at least r apart. But here the problem is more subtle. The next thing you do is look at the homology. In this course setting, you want to look at the coarse homology. I haven't said what is coarse homology yet, but I will come to that in later. So the next thing you try to do is try to look at the coarse homology of these things. But the problem is this space doesn't reflect the homology, the coarse properties of the complement. So really what we are interested in trying to find out the coarse property of this complement of the diagonal. Okay, but just deleting the tubular neighborhood and looking at the complement doesn't give you the right picture in the coarse setting. And the reason you can think about this example, for instance, r square. If you think about r square and look at the diagonal and take any neighborhood of the diagonal, it still remains the same as r square, right? Coarsely, it is same as r square. So you don't change anything, no matter how big you delete how big tubular neighborhood you delete from r square. Okay? But that was really different in the topological setting, right? When you delete a diagonal in the topological setting, you have a nice space where you have non-trivial homology, which gives you nice things. So the problem, what's the idea to get rid of this thing? So really, that turns out to capture the coarse property of complement, what you need to look at is the sets which are coarsely disjoint from the sets you are deleting. So here we are trying to delete that diagonal, and so we have to look at the set B, which has this property that any neighborhood of B intersect any neighborhood of the diagonal in bounded set. Okay? So you can think about the analogy you have in the topological setting. Complement means intersection should be phi, right? And here we are saying that coarse complement means the little bit big neighborhood of them should intersect in bounded set. In coarse setting, bounded set should be assumed to be the empty set. Okay, so I'll make it precise in the next slide. So I haven't told you what coarse homology is. So the coarse homology was defined by Rove, and what you do is you look at this. The n quotient is a map from n+1 tuple to R. So you really think about this n+1 tuple as vertices of n simplices, and so you are assigning some number to each of this n+1 tuple, just like usual quotient. But you have this support condition that the support of F should intersect the diagonal. So there is also a diagonal sitting inside x to the n+1, where all the n+1 coordinates are same. That support of F should intersect any neighborhood of the diagonal in a complex. And this boundary operator is the same as usual. So that is a coarse invariant. So if you have two spaces which are coarsely equivalent, that homology would be isomorphic. So now, joined with Okun, we actually generalize this to define coarse homology of the complement. So what you do there is, as I said before, so you look at, so let's say you have a subset A in X, and you want to measure the coarse homology of the complement. What you do is you look at this collection of set which are coarsely disjoint from A, meaning that property, and then you look at the following quotient. So you look at all such function so that when you restrict it to any coarsely disjoint set from A, it satisfies this property of Rho. Okay, so that's the quotient here. So you look at all the quotients which is coarse when you restrict it to any coarsely disjoint subset from A. And now you have all this subset E, and you have this inverse system. And if you're like me and scared of inverse limit, here is something that might make you feel better, which is, well, for nice space, if you have a uniformly contractible space, then uniformly contractible means any ball of radius r can be contractible inside ball of radius s, and this correspondence between s and r doesn't depend on where you take your center, the ball. And for this kind of spaces, for example, any universal cover of any closed spherical space is an example of uniformly contractible space. And so for those spaces, that's how the coarse homology of complement of any subset looks like. So what you do is, well, you take bigger and bigger neighborhood of that subset and look at the complement and look at the singular homology, and that's the limit would give you the coarse homology of the complement. But that only for uniformly contractible space. Okay, so now once we have this right coarse homology for the complement, I can now define coarse homology of the configuration space. Well, remember the coarse configuration space should be really x squared minus that diagonal. So I'll just define the coarse homology of the configuration space by considering all the quotient which lives here. Okay, this quotient. But now remember, in the topological setting, configuration space means the Z2, the quotient space. And so to get the homology of the quotient, you can look at the equivariant quotient on the cover. And so that's why this F is Z2 equivariant. That's condition terms. Okay. All right. So that's how you define coarse homology of the configuration space. And now give you an example. So for Rn, the coarse homology of our configuration space of Rn is Z2 when in the degree between 2 to n. Okay, and it's little annoying that at degree 1 it is 0, and the reason is, you know, it corresponds to reduced homology, and that's why that's what the reason for that. But it's okay for us for our application. So that's the configuration space of Rn coarse homology. In particular, it is 0 when the degree is bigger than n. Okay, and which we will use in the next slide. Now we are in a good place to mimic the Van Kampen's construction in the coarse setting. So now let's XPX metric space, and let's you have a coarse embedding from X to Rn. We do the same thing. Let's choose another embedding from Rn to R infinity. Now you have this composition of maps, and this composition of maps, it takes, well, it's not difficult to prove that these maps induce a map between the coarse homology of the configuration space. Okay, and again we do the same thing. This we know that is Z2 for all n between 2 to infinity. By the previous slide, I saw this example, and so you can pick this generator from that here, and this one is 0 for all degree above n, and so you have this composition is 0 when you apply to eta to the n plus 1. And the fact is, the main, I guess the main point is, again, this map depends only on x, not on f or I, and so I can denote it by this. So this is an intrinsic class to x, and so again, just like the Van Kampen obstruction, I get this following, that x coarsely embed into Rn. Starting from there, you get that some class vanishes. Okay, so that is the obstruction in the coarse setting. And so the last slide I'll go quickly. So I have this obstruction there. So a few examples. So if you have a finite complex K, and you know the fan Kampen, the topological obstruction is not equal to 0 in degree n minus 1, then the infinite cone, if you take the infinite cone with this property, with this slight assumption on the on some choice on the metric of this infinite cone, this class in degree n plus 1 is actually non-zero. So that just means that thing, cone infinity of K, cannot embed inside Rn if you know the K is bad enough. And same thing you can say for coarse PDN plus 1 space, which is, you can really think about uniformly contractible n plus 1 manifold. This obstruction is non-zero, so that just means uniformly contractible n plus 1 manifold cannot be embedded inside Rn. And so these examples actually gives you recover some results which was proved earlier by Bispina, Kapovich, Kleiner, who showed that if K is a finite complex and this fan Kampen obstruction is non-zero, then this infinite cone doesn't admit coarse embedding into Rn. And similarly, the second example here tells you this result by Yoon, which says that if X is proper, uniformly contractible n plus 1 manifold, then it doesn't admit coarse embedding into Rn. So I'll stop here. Thank you.
Thank you. Let's thank our speaker. Do we have any questions? Please mute yourself or put them in the chat.